So my research is on the detection and prevention of adversarial attacks on connected and autonomous vehicles. I'll be doing the presentation and then I'll be having the first go on loop, so hopefully I'll get the narration and everything to record properly. So we have connected and autonomous vehicles. They're self-driving cars and they use machine learning to be able to operate independently. And these machine learning models that they are driven by can be attacked through a variety of means. And this research paper is about defense against these attacks, and specifically the deep billboard attack that we will be discussing. So by 2045, cabs are estimated to occupy a much larger percent of the vehicles on the road, and research has shown that there are many ways that cabs can be maliciously affected. And again, focusing on this deep billboard attack, where they create a billboard that causes the steering angle of the vehicle to become very abnormal, so it'll cause the vehicle to veer to the left or to the right, whatever they choose. And this obviously can be used to do something like crash a car or steer it off a cliff or into oncoming traffic, so it's very dangerous. So the objective of the research is to design some mechanism that can censor the malicious parts of the image so that the vehicles can operate safely. So we have images with some sort of malicious content, and we need to create the mechanism that will remove the dangerous parts. And there's a lot of research already that discusses how you can prevent or protect models against these attacks, or machine learning attacks in general, but some of them require something like white box views inside the model. So if you are able to adjust your model, so the driving one, then it's a little simpler, but we don't want to be messing with the internals because we don't know if our changes are going to introduce uncertainty into the behavior of the model. So it's we want to treat it as a black box. And then other research has shown that you can create mechanisms to identify whether or not images contain attacks or if they are safe or not. But just because we know an image isn't safe, either we turn the camera off or we keep feeding the unsafe images to the model. So just knowing it is or isn't safe isn't enough to keep the vehicle safe. So for the attack, the deep billboard attack uses gradient descent to find the combination of pixels that causes the most deviation from the normal steering angle. And it needs a sequence of images of a vehicle driving past the sign, and then these images need to be labeled with the positions of the billboards within the sign, and then it can create this attack image. And then once observed, it will cause the vehicle to veer to the left or to the right, whatever the attackers want. So we propose a framework that will have two components, the part that identifies the attack and then the part that censors it. And images are sent through the pipeline before being interpreted by the driving agents. So we have some source image that enters the pipeline, and then it passes through the image segmentation component where it will identify which pixels contain malicious imagery. And then the sensor just uses that information to block out those pixels. And then it should be safe for the driving model to consume. There's other approaches that can substitute or augment the components in our pipeline. So the watershed transformation can segment touching objects in a grayscale scene, which is not useful for finding the attack billboards, but it is something that can be useful when we generate the data set, which will later be discussed. And random forest is another method of image segmentation separate from the machine learning approach that we use, but it's good to know the other methods that are out there. And then there's also a technique called feature density inspection, which works by identifying outlier information for each class to help reduce the chance of misclassifications once trained. This is potentially viable, but may require tinkering with the internals, which again we want to avoid because we don't know if we're introducing uncertainty. So when we are acquiring our data set, we need a lot of images to train our model. So we need a data set that contains attack images and has labels defining the pixels that the attack billboards occupy. Unfortunately, the research that introduces the attack is very novel, so there's not a data set existing for it. And then even further, there's not really a data set that just has an abundance of billboards that are labeled, so we have to discover that ourselves. So we need to find a data set that has the scenes labeled and has a separate class for billboards, which a research paper has helped identify data sets that contain separate classes for the billboards that we can use to create our own data set. So it's not the original data set isn't focused on billboards, but we can use it to create a new one that is. So we need a lot of attack images as well to post on the billboards. So we ran the original research paper to generate a bunch of different attack images that we can then apply to the billboards. Usually the attacks require the entire scene to be considered when creating the attack for that billboard, but we ran into limitations with the original research paper, so we had to generate all the attacks beforehand and then paste them onto different billboards. So they won't work as attacks, but they'll look the same, and that's the goal for the data set. So once we have the attack images and then the billboards, we need some mechanism to apply the attacks onto the billboards. So if we start with the labeled image, we can isolate the billboard shapes to create a mask. And from that mask, we can get the contours, which are the points that define the perimeter of the shape. And then we need to find which of these points corresponds to the corners so that we can apply a transformation to get the attack images on to the billboards. This reduction of points is a fairly tricky step, but once we have just the corners, we can apply a transformation to get the images onto the billboards. So there's some challenges with creating the data set. So how do we reduce the points to just 4? How do we know that we're splitting the billboards properly? And how do we know what the original scene kind of looks like? So we'll start with the contour recognition problem. If we have a shape and the points for the perimeter, we can say maybe we can just take the minimum and maximum points to find the corners, and that works until you introduce perspective and other warps into the situation. So if the billboard's at an angle or seen from an angle, that affects the way it needs to be determined which points are the corners. So if we go about it the wrong way, then we end up with the wrong shape for our billboard when we're applying the warp. So a different approach is smoothing, where we take all the points on the perimeter and we identify which points can be removed until we are left with only the corners. So if we look at them, we know which points are the neighbors. So if we see that the angle between them is flat, then we can prune those points until we're left with only 4. And that is how we're currently reducing the points to get our proper transformations. But another issue is that when we're given these scenes, we don't know how the billboards are overlapped in the scene. So if we see a shape like on the left, we don't know that it's supposed to be split like it is on the right. So that affects how we apply the transformation. So there's a lot of challenges with this data set creation process. And of course, if there's something like a light post in the way when you look at the billboard, we only know that there's 2 rectangles. We don't know if they're supposed to be the same one and there's something in the way, or if they're supposed to be two different billboards. And that also affects the way that we apply the attack imagery. So we trained the models on Google Colab with the free tier, and that gave us a Tesla T4 GPU, and we trained for 5 epochs, and it was fairly quick. So under 10 minutes to get the full model trained. And we have 2,400 attack images. And each of those scenes can have more than one attack within them. And we trained 2 models, one that uses a SegNet architecture and one that uses a UNet architecture. So given a scene with an attack billboard on it, the models are able to successfully identify which pixels contain the attack, and they do this really well. So after only 5 epochs of training, in under 10 minutes, the model can already identify the attack. And then from here, it's just passed through a sensor to remove the malicious pixels, and then it's safe for driving. So for more standard metrics on how well the models perform, the precision and recall are both over 99%. So more rigorous training can still be done. We can get more images and improve the test train split and get just a better data set, but already we are able to train a model that can successfully identify attacks in 99% accuracy. So we have successfully created a pipeline that will allow for the sanitization of images before they're fed to these driving models. So that was the goal, and we succeeded. And then future work, we can work on improving the dataset generation process. We can add more images, improve the billboard detection, and then of course we can add more testing and see if we can run this real time. Can we optimize it to the point where it can be used to protect a vehicle from the attack that was seen at the beginning?